Welcome to my talk on architecture for a data and AI-driven world. My name is Jan Bosch, and I will introduce myself later in this presentation. I often like to start my presentations by showing a quote. So here's one of them that I think really captures what I will be talking about. This is from Elon Musk, and he says that I think it's very important to have a feedback loop where you're constantly thinking about what you've done and how you could be doing it better. And in the age of ops, which is what we're going to be talking about quite a bit today, I think that this is one of the important things, that in ops, if it's DevOps or data ops or ML ops, we have feedback loops that we perhaps didn't have access to earlier. And I think that that's going to be a very important part of software engineering going forward. And I'm hoping to focus a bit on that during this presentation. So again, I often like to start with some key takeaways that I believe are helping to understand what is happening in the world and to put things in context. And the three takeaways that I wanted to really stress with you today is that one, software engineering, in my opinion, is really changing. We're moving from a world where everything is basically centered around software and traditional requirements-driven or specification-driven development to a situation where software development is much more complemented with data-driven and AI-driven approaches. And not only that, we're also moving towards a world where the feedback loops are much faster than what we've seen in the past. And this then results in DevOps for software, data ops for data-driven practices, and AI or ML ops for artificial intelligence-driven functionality. And that has implications on architecture, I believe. One of the implications is that fast feedback loops allow us to work in a much more quantitative fashion than what we've been doing in the past. And if we talk about measuring the effects of architectural design decisions or measuring the effects of architecture refactorings, for instance, if you talk about architectural technical debt management, earlier we did not really have the opportunity to do this in a quantitative fashion, so it led to a lot of reasoning about things. But the ops world that we're moving towards allows us to work much more quantitatively. And I think that that's a good thing. The other thing that I believe is that data-driven and AI, machine learning, deep learning functionality add new types of architectural challenges that we need to address as a community. And I will bring some of those up as we go through the presentation. What I was hoping to cover in this talk is first give you a little bit of an introduction of who I am and where I come from, so you have a bit of an idea of what my perspective is that I have in this. Then I want to spend a few minutes on the concept of digitalization. I mean, what is that actually meaning? What impact does it have on industry and on companies, so that you have a bit of a better understanding? And why I think that that's important is because architects, even though many architects, especially PhD students, may think that it's only about technology, for me, architects operate on the boundary between business strategy and technology strategy and need to have a good understanding of in what context their architecture will operate. Then I'll move into the age of ops, and I'll separate that between DevOps, data ops, and ML ops. And for each of these three, I will discuss some implications for software architecture, as this is a software architecture summer school. Those are perhaps also some of those things that perhaps additional challenges that we can discuss during the session on the 15th of June that is coming up. Finally, I couldn't resist but spend a few minutes on our AI engineering research agenda. It's a little bit tangential to what we're doing around architecture, but I still think it might be relevant and interesting to think about and to learn a little bit more about. So very briefly about me, I used to be a young and innocent professor of software engineering in the 90s and the early 2000s. In the early 2000s, I got a call from Nokia, and they managed to convince me to take a job as head of the software and application technologies lab at Nokia Research Center at the time, around 200 people at that time. I did that for a number of years. Then I got an offer from Intuit. You may not know the company if you do not live in the US, but Intuit is now, I think, around 10,000 people, 6-7 billion in revenue, in the personal financial software space by and large. I was VP engineering process there and had several other responsibilities within the company as well. For the last 10 years or so, I have returned to academia. I now work at Chalmers, even though I also have a part-time appointment at the Technical University Eindhoven. I run something called Software Center that I'll introduce in the next slide. And besides that, I divide my time between some consulting work, some boards that I'm part of here in Sweden, and some angel investing. So if any of you have any intentions of starting a company, we can always have a chat if there's some way in which I can become involved or not. The day job that I have these days, where I spend most of my time, is acting as director for Software Center. Software Center is a collaboration between 16 international large companies and 5 universities. We have large Swedish companies such as Volvo Cars and Volvo Trucks. We have also Scania, another truck brand from Sweden in the Software Center. Of course, Ericsson, a Swedish telecom company, #1 in the world. Access Communications, which is part of Canon. SenseAct, a part of Volvo Cars, looking into autonomous drive solutions. SEFT is a Geely company, so in the same company as Volvo Cars and SenseAct, but it's China Europe Vehicle Technologies. Some of you may know that Geely owns around 10 different car brands, including Volvo Cars, but also quite a few others. Saab is another Swedish company. This is the defense company, but we also have companies from other countries. We have Siemens and Bosch from Germany. Wärtsilä is from Finland. Jeppesen is a US-based company, although we work mostly with their daughter site here in Gothenburg. And then, of course, Denmark, we have Grundfos, a company that builds and manufactures more than 18 million pumps a year, and Dive, a company in the marine wind power and land power based solution. So all of these companies are focusing on the same challenge, which is to significantly improve the digitalization capability of the European software-intensive systems industry. We do that by conducting work in a number of different areas. We look into work around continuous delivery, so that we view as continuous integration, continuous test, continuous deployment, the whole DevOps space, etc. We also look into software architecture, specifically around architectural technical debt management, API management, those kind of questions. We do work around metrics. Miroslav Staron, one of my colleague professors, is leading that theme and doing a very active job there, and has done wonderful work around metrics. There's work around customer data and ecosystems, which is headed by a professor from Malmö University, Helena Holmström Olsen. There we look into what can and should companies do with all the data coming back from the field, and also how should we think about the business and software ecosystems in which we operate. And then the final theme, which we started about a year ago, is around AI engineering, and that refers to all the challenges that you need to address in order to go from a prototype or experimental machine learning model to a industry strength production quality deployment of machine learning and deep learning models in our broader software intensive systems. Most of the companies that I showed that are members of Software Center started their lives as metal bending companies or mechanical engineering companies, but we do have quite good connections with several other what we typically refer to as digitally born companies. So Booking.com is of course one of them that we've had quite a bit of interaction with over the years. Rovio is a company that we talked more a while back, but still an interesting company, the company behind Angry Birds. King is the company behind Candy Crush, as well as several other mobile games. Spotify, I think many of you know. Klarna is a company that provides credit to people that buy things online. And some of our PhD students or former PhD students are either working at Microsoft or have visited Microsoft in a visiting capacity. So that's and we take some inspiration from those companies. So that's a little bit of my background and what I've been spending my time on recently. If we go to digitalization, first, I think it's important to be clear on definitions. So we define digitalization, we often use the Gartner definition as the use of digital technologies to change a business model and provide new revenue and value producing opportunities. It is the process of moving to a digital business. Now, what is important to understand, especially for companies that started their life in the mechanical space, is that we're moving from a world where first it was all about mechanics, then we added electronics to the mechanical systems, and that happened typically in the 80s and 90s. Then we started in the 90s and later on to add software to those systems. More recently, data and artificial intelligence are the next generations of technologies that are becoming added to our systems in the field. When we talk about digitalization, what we are referring to is the three digital technologies. So software, data, and artificial intelligence. Those are the key enabling technologies in the context of digitalization. There are three important things that are happening. The first to understand is that as we move from only being mechanical and adding electronics and then software and then data and then AI, the old technologies do not disappear. They still remain part of the products that we build, but it becomes increasingly difficult to differentiate yourself in mechanics and electronics, and to some extent even software. And increasingly the differentiation is taking place in software, data, and artificial intelligence. That also leads to a shift in business models very often. When I focus most of my energy on the atoms in a product, the mechanics and the electronics, it tends to lead to a situation where I have more transactional business models. So I will buy a product, I will use that product for a period of time until it has deteriorated to the point that I need to replace it, and then I buy the next instance of the product. In more digital products, or when the product value is mostly realized through digital means, what we see is that the business model often changes to more of a subscription model or a more of a continuous business model, where I increasingly generate value through a continuous model rather than an upfront payment model. From an ecosystem perspective, what this means is that every time I include a new technology, I need to add new partners to my system. So when I add software, I need to add partners that help me with software or provide commodity functionality in software, or that help me innovate. When I move to data, the same thing happens. And what we now see happen is that there are quite a few players in the AI space that large and established companies are working with. The other is that it leads to an evolution, or sometimes, according to some people, even a revolution in the way that we work. So our ways of working typically now initially we moved from traditional software deployment to DevOps, then we add the data, we move towards data ops, and then we move to ML ops. And I'll be talking about that a little bit more in this talk. Another thing which is important to realize is that this is not something that is purely technical or that only addresses some functions within the company. It basically changes everything in the company. And over the last few years, together with a colleague, I have been studying the software center companies and looked at how do these companies evolve. Now, and what you can then see is that there are four main dimensions of change that are taking place. The first is the business model dimension that I already alluded to in the previous slide. But what we see is that companies move from traditional product sales, you buy a box, to I give access to my product as a service, to I start to increasingly offer complementary services around products. For instance, if you go to some of the truck companies here in Sweden, we see that they are increasingly focusing on offering all kinds of services around their trucks. For instance, they give advice to drivers where they should buy their fuel, where they should take their rests, where they should eat, etc., etc. So all kinds of services around the product itself. Then you move towards a customer KPI-based business model. So in the case of logistics, for instance, I do not sell the customer a truck anymore, but rather I monetize my systems or the solutions that I offer my customers through me delivering on and improving the KPIs of a customer. So I may be paid for every successful on-time delivery. And for those of you that have looked into service level agreements, this is typically where you talk about those, but the main difference between this business model and traditional SLAs is that in SLAs, you only get punished for not delivering. You don't have an upside typically. So if you do better, you don't get paid more. In these customer KPI-based business models, you typically get paid more when you deliver more value to customers. The final one, which is a really interesting one, is that we then see that once you have that in place, you can also start to look at all this data that I'm generating from my customers. Are there other parties that are interested in monetizing or getting access to that data? So one of the examples that is often used in logistics is all these trucks on the road, they all have GPS and they have accelerometers in them, which means that every truck is basically a driving sensor for road quality. So if you have a lot of potholes or other issues in roads, the accelerometer will provide much more aggressive data. And you could imagine that road authorities, for instance, would be interested in buying this data from, for instance, truck companies in order to understand which roads need maintenance or not. And what you can then see is that the other dimensions, such as the data exploitation dimension, are then changing as well. With every step that I go up, initially I mostly use data for quality assurance and diagnostics. Then I move to data to measure product performance. How's my product actually performing in the field? Once I move to the middle step, it's typically using the data from one customer for generating value for that customer. To the fourth step, I basically take the data from my entire customer base and I start to provide individual data-driven offerings for my different customers. So this is where you get into a situation where you can, for instance, tell a customer how well it is doing compared to all the other customers. So you can do things like benchmarking and other kinds of things. And then I already talked about the data for the secondary customer base. But the interesting thing is that you may then start to put instrumentation in your product to collect data that is actually never useful for the user of that product. It is only useful for the secondary customer base. In the product upgrade dimension at the bottom, you can then see that initially I focus on the mechanical and the product as a physical item. Then I move towards reactive software updates, typically when I have quality issues and stuff like that. Then I move in the middle one to a real DevOps approach where I continuously try to push software. The next step after that is that I expand the upgrading to include not only software, but perhaps also electronics and other hardware. And then the final stage is that I have a fully digitalized offering where, similar to when you have an iPhone, when you switch phones, nothing really changes except that the phone becomes a little bit faster and a little bit better. But other than that, by and large, it is the same digital offering that that becomes better on a continuous basis. The final dimension is the AI, machine learning, and data, the deep learning dimension, where initially I only use data for human interpretation. The second stage is that I have static machine learning models that are trained on fixed data sets. Then I move into AI coming integrated into the DevOps model. The fourth stage is where I use machine learning to allow for mass customization. And the final stage is where the system can do fully autonomous experimentation. And then you can think about techniques like reinforcement learning, where every instance of the product is trying to continuously get better and deliver more on what it is supposed to do. So that was digitalization. What I now want to do is to dive a little bit more into the core of the presentation, which is what happens in the age of ops and what are the implications for software architecture. So the first thing to realize is we wrote a few years a paper in which we described the holistic DevOps framework. What is important here is that you have to understand that the traditional requirements-driven development will not go away. That is still something that is that needs to be present, but it is going to be complemented increasingly with two additional approaches to software development. The middle one, what we refer to as outcome or data-driven development, that's where you have a hypothesis or a set of KPIs that you want to improve. And as a development team, you basically develop hypotheses on how to add value, and you then, through A/B testing and other approaches, experiment your way forward to figuring out what is the best way of delivering or improving these KPIs. Then you don't start from requirements, but what you do is you start from outcomes. So you say, I want to improve conversion on a website. I want to improve fuel efficiency in a car. I want to improve throughput in a telecom system. And rather than saying this is how you should do it in a requirements-driven way, you say to the team, this is the outcome or the KPI that I want to see improved. Go and experiment and figure out what is the best way of driving that forward. The third approach is what we call AI-driven development. I think many of you have looked into that, but the idea is that I have a large set of typically labeled data, because most AI approaches these days are supervised learning. I train the model and then I deploy it in the field. One of the important things here, however, is that there will be in systems already now, and increasingly more so in the future, there will be software modules or components that are developed by all three different approaches. All these components are subject to DevOps. All these components are expected to generate behavioral data so we know what's going on. And all of this will basically operate in a ops loop, whether you call it DevOps or something else. And that's why we also divide things into data DevOps, data ops, and ML ops. If we then dive into DevOps, I think that one of the almost 10-year-old models that we still use quite a bit is this approach. This describes how companies evolve over time. So starting from traditional development, almost all companies these days have now adopted agile development practices. For those of you that have experience in industry, may have been surprised at how hard it is to get an organization to work agile, but in practice, this really is the most simple change. The next step is that you move towards what we refer to as continuous integration. In continuous integration, you basically combine the R&D teams and the verification and validation department, and you have a solution where you can, whenever anyone checks in code, you can very rapidly learn whether the system is still at production quality or not. So teams get very fast feedback on whenever they have issues. Once you're done with continuous integration, you are able to move to the next stage, which is continuous deployment, where I push out software on a frequent basis, typically the same frequency as the sprint length that I have. So, but at least every 4 weeks, there is a new version of software that is basically being pushed to the field. And this is, of course, initially something that started off in the software as a service world, but we increasingly see that also embedded systems companies are moving in this direction. For instance, Ericsson these days is pushing software in live base stations to customers every 2 weeks for all the customers that want it. Once I have continuous deployment, I can start to move to the next stage, which is I start to use my R&D as an innovation system. So then I can decide to do things like A/B testing out in the field, where some customers get version A of a feature, other customers get version B of a feature. I measure how the customers that get version A are performing, how customers getting feature version B are performing, and based on that comparison, I decide whether I deploy A or B to everyone, the typical classical A/B testing approach. The other thing, which is quite important and has several architectural implications as well, is that when you move to DevOps, companies that traditionally used more of a customization approach to generate the different products need to move to a more configuration-based approach to generate their products. And I can see that I'm going a little bit slow in the presentation, so I'm not going to deep dive on this. But what is important here is that for a product family, for those of you that look into software product lines, I basically have a single code base, and I have fully automated product derivation that allows me to, out of that single code base, generate all the product alternatives, run each product through the continuous integration and test environment, generate defects that may surface into and put them in a defect backlog. Of course, I also have a refactoring and a runway backlog where I do architecture refactorings and improvement on the infrastructure. And of course, I have a feature backlog. And those three backlogs need to be combined into a top-level prioritization for development teams. The architect team here is then mostly concerned with, of course, guiding teams to implement features in a way that minimizes the adoption or the prevalence or presence of architectural technical debt, but also to identify refactorings that are required to keep the system fit for purpose. Another factor which we think is quite relevant and important and not used nearly as much as what we would like to see is what we have defined in the HyPEX model. And this is important because here what we basically do is, rather than building a feature in one go, top to bottom, everything including the kitchen sink, what we basically say is build features in an iterative, sliced manner in order to determine that what you expected this feature to deliver in terms of value is also what is realized in terms of value. So what we see here is that out of the feature backlog, I pick a feature, and the first thing that I do when I go and add that and plan the adding of that feature to the system is that I define the expected delta in behavior that I expect to see when I add this feature to the system. And this can be changes in behavior from the customer, or this can be changes in behavior from the system. Once I have defined what I expect to see, I can then go and build the minimal viable feature. That is the first 10-15% of that feature that I can then add to the product because I have DevOps in place or a continuous deployment in place. Once I have added that minimal viable feature, or the first slice of the feature, I can then start to measure what is the actual behavior. How did the behavior of the product or of the users actually change in response to this? And then I can start to do a gap analysis between what I expected and what I actually see in practice. And based on that, I basically then have 4 possible outcomes. One, I've built 30% of the feature. I got everything I wanted. There's no need to build the other 70%. That's one outcome. Another outcome is I added the first or second slice. I see totally nothing of what I expected to see. And that then results in a situation where I should abandon the features, so just not add it, just remove the first parts of the feature and move on to the next feature. A third alternative is that I see some movement, but not as much as I wanted to see. And then I extend my minimal viable feature. So I go through the loop where I add more and more of the feature to the product. And the fourth alternative, which actually also happens, is you do see movement in the data after the first and second slice, but it's very inconclusive. And that often is an indication that the way that you're realizing the feature is not the way that the users want to see it, or the way that generates the best impact on the system. And you should then basically drop your current implementation and try out an alternative way of realizing that feature. We believe that this is really important because our research, as well as the research by others, shows that order magnitude somewhere between half and 2/3 of all the features in a typical system are never used or used so seldomly that it isn't worthwhile to the R&D effort that was invested in the product was not worthwhile. In this context, we've developed something that we've called value modeling. Here you basically try to describe the different outcomes that you're looking to accomplish through this development. And I don't have, in the interest of time, I will not deep dive on this, but the idea basically is that I have lower level team and feature level value factors that basically feed into higher level product and system level value factors that then in turn feed into higher level business level value factors. And there's a whole process around this. And if you have an interest in learning more about this, we can discuss this either in the upcoming session or offline. There are a number of implications for architecture that I think DevOps brings. The first is, as I already mentioned, these fast feedback loops that DevOps basically creates allow us to adopt much more quantitative approaches to evaluating architectural design decisions. I think that that's really an important takeaway, because we have traditionally done architecture design decisions much more based on experience, different forms of assessment techniques, etc., etc. But now we can go and actually measure things at systems in the field, which I think is a really healthy way forward. The second implication for architecture, I believe, is that architecture technical debt management becomes even more of a continuous process. Of course, we already were always talking about it as a continuous process, but in a DevOps context, we can handle it even more as a continuous process, and we can add quantification to it. So we can actually measure if the effects or the benefits that we were hoping to get from a refactoring or something along those lines is actually realized or not. Of course, some of the architecture refactoring affects, for instance, maintainability of the system. That is not something that you can instrument the system itself with, but you can still instrument the development process and collect data even on the development process in order to determine if your refactoring efforts have had impact or not. The final one, which leads to discussion in many of the companies and research communities that I'm part of, but interestingly, continuous integration and test does not only allow you to test the functionality of the system or the non-functional requirements of the system. For at least a subset of architectural rules that we want to have in place for the architecture, we can even encode these architectural rules as test cases and basically cause failing test cases whenever a team violates architectural rules. And this is a way in which you can enforce architecture and minimize the gap between the designed architecture and the architecture in use to a much larger extent than what we perhaps have seen in the past. So I think that's an interesting development. Second topic that we're going to talk about here is the notion of data ops. So in data ops, let me first define it a little bit. Data ops is a general methodology to design, implement, and maintain a distributed data architecture. It combines or blends software development techniques and agile management principles into data analytics pipelines. And data ops is intended to shorten the time required to build insights from raw data. So from raw data to the insights that you would like to get out of the data, how do you shorten that time as much as possible? I don't want to spend too much time here. This is a paper by one of my PhD students, actually two of my PhD students, three of my PhD students here, around data ops based on a study at one of the software center companies. And one of the things that we did as part of that work is to basically create a maturity model on how companies can move from a much more manual and ad hoc form of data analysis to semi-automated data analysis, to agile data science, to continuous testing and monitoring of data pipelines, to full-fledged data ops. And again, in the interest of time, I will not deep dive on this, but if you're interested, you can take a look at the paper or we can talk about it in the upcoming session. Another piece of work done by Aishwarya Rai is around data pipelines. We see that many companies are really struggling with building up and maintaining reliable, high quality data pipelines that result in data that you can actually trust, both for data analytics and for machine learning. What we did is we basically developed almost a domain-specific language where we describe the different elements in a data pipeline, as well as the types of validation and tests that happen at each stage in the pipeline, either in the box or in the connection between different boxes. This is just one example of a conceptual data pipeline. We have several more, and this is ongoing work where we try to help companies improve the way that they work with data pipelines, because for most companies, data and data pipelines, and especially the continuous form of data pipelines, is relatively new and still quite a challenge. We've done a bit of work. This is a paper from a few years ago where we tried to capture some of the data management challenges. I mean, it says for deep learning, but in practice it is, I think, much more broadly applicable. And this is based on at least 6, but I think we have more like 12 case studies these days, where we, in the different phases of data management, so collection, exploration, pre-processing, preparation, testing, deployment, and post-deployment, identified what are the key challenges that companies and specific systems in companies are experiencing around data. And here you see things like lack of metadata and data granularity, to shortage of diverse samples. And this is a typical case that you see, for instance, in predictive maintenance. Most of the time, systems are operating just as they should, and only very seldomly do things start to break, and do you get data that indicates that predictive maintenance is required, and then you run into shortage of all kinds of samples. Also, you need much higher statistical understanding for many people. Data quality is an issue, data dependencies is an issue. So the same things that we're talking about in software architecture about separations of concerns and decoupling and minimizing dependencies, that also happens on the data architecture side. There are other things around tooling, feedback loops, etc., that I think are relevant problems. Another piece of work that we published in ICSI this year actually is around data validation and how one automates automatic data validation or data validation. Here we developed an approach where we can run tests in data pipelines using tooling that we've built on the feature. So if you have your data records, an individual feature in the data record can be evaluated. So in there you can look at missing values and other kinds of things. Then you can start to look at the data set as a whole. You can start to compare cross data sets. So for instance, if you have 2 data sets that should have the same statistical distribution, if one data set is starting to shift its statistical distribution and the other one does not, you can typically figure out that something bad is going on. And also in data streams, you can have a window over the data, and you can run all kinds of analyses, not just on the individual data items or the individual data records, but you can also determine in the data stream that the window that you're looking at is shifting in certain ways, the means or the standard deviation or the statistical distribution or other things are starting to change, and that can then be indicative of issues and concerns. And that allows you to validate your data in a much more automated fashion. If we look at implications for architecture when it comes to data ops, there are, I think, 3 things that I wanted to highlight here. The first is, in addition to the traditional software functionality, software architecture now needs to cover data generation, data processing, and data collection, and the other things that you typically find in a data pipeline as well. That needs to become a concern of the software architect that needs to be addressed. Second, we need to address architectures to allow for easy instrumentation of functionality. I mean, we all know that many systems are generating vast and enormous amounts of data, but in practice, we very often see that whenever we have a certain question that we're looking to get answered, the data that we would need to answer that question just happens to not be available. In the gigabytes, terabytes, petabytes that we have available, just that data that we needed happens to be not available. And in a data ops, DevOps context, you can then add instrumentation of the system and start collecting the data that you would actually need. But that should be easy. That should not be a very elaborate and complex process. The third topic, which I think is building on the first 2, is that this whole notion of data validation and data quality management should really be inherent in the architecture. How do you deal with those kinds of questions? This is actually quite important because virtually every company in the software center is struggling with data quality issues. From an academic perspective, this may seem like extremely easy and trivial, but in practice, it proves to be surprisingly difficult to deliver and generate high quality data that is actually generated in such a way that you can use it for useful purposes. Good. Last topic. I can deep dive on this quite a bit on the previous point, but I need to move on because this presentation is starting to get too long already. MLOps is where I wanted to spend a little bit of time on. If we talk about architectural challenges in machine learning, I think that there's no better place to start than this paper from a couple of years ago, written by people from Google, where they showed what kinds of technical debt they had been experiencing in machine learning systems. This is in NIPS or NeurIPS, it's called these days. But the idea basically is that the little black box in the middle is the machine learning code. Everything else around it are boxes that are required for that little machine learning model to actually function and operate in an industrial production context. This is important to realize because it brings quite a number of architectural challenges with it that we need to address as a community, I believe. The second thing, and this is maybe clear for all of you this far in the talk, but if we look at the main stages in a machine learning, deep learning development stage process, you see first you need to assemble the data sets, then you create models, then you train and evaluate, and then you deploy the model. And of course, there are loops in the creation of model and the training and evaluating. I often iterate. And also in a data ops, DevOps, ML ops context, I also deploy on a frequent basis. And the most recent deployment is often generating the data for the next iteration of the model. Everyone and their brother talks about the model creation, the various models that you can use, different algorithms that you can use. Many papers in AI have a tendency to say, I have a small tweak on an existing algorithm that for this particular set of data or this particular type of data performs slightly better than all the other things that were already there. So this whole loop of creating models and training and evaluating is where most of the attention goes. If we look at an industrial perspective, however, we see that the assembling the data sets and the deployment of models in a production quality environment, that is where all the effort goes. The little part of creating the models and training and evaluating is actually the easy bit. It is getting high quality data, getting proper deployment in place with all the monitoring and logging and everything else around it, and then getting the loop up and going. That is what is hard in machine learning and ML ops contexts. We've developed a bit of an ML ops framework. This is a PhD student at Malmö University, supervised by one of my colleagues, Helena Holmström-Olsen, as first advisor and me as a second advisor, where we look into a framework where we can see three loops, basically, if you want. There is a data pipeline iterative process. There is a modeling pipeline process, and there is a release pipeline process. This paper is currently submitted, but once we get it accepted, I happily share it with you. And there you can look at the different stages and different activities that you can find. So initially it's about data acquisition and pre-processing and feature engineering. In the modeling pipeline, it's about experimentation, optimization, and evaluation. And in the release pipeline, it's about packaging, it's about validating, it's about deploying, and it's about monitoring. In 3 years ago, we wrote the paper. I think 4 years ago, we did a study around machine learning and what are the key challenges that we saw. This was with one of the companies I'm on the board of, Peltarion, that builds a totally amazing platform for deep learning solutions. And if you're interested in it, I think you should really go and take a look and maybe take some of the free tutorials to learn a little bit how to build deep learning models. But what we did was we evaluated the kinds of challenges that many companies are experiencing. We categorized them around development challenges, production challenges, and organizational challenges. And we put them on a two-dimensional space from low to high business impact and from easy to solve to hard to solve. And then you get all kinds of things around effort estimation, privacy and safety, unintended feedback loops, dependency management, and one of those typical architectural challenges, testing, transparency, monitoring and logging, experiment management. Those are some of the topics that we then identified. We followed this up with a paper 2 years ago, which was around, again, several cases that we studied where we looked at what are the key challenges in the first stage of experimentation and prototyping, the second stage of non-critical deployment, critical deployment, and cascading deployment. And then for each of the 4 stages in the data science lifecycle, so assemble the data, create the model, train and evaluate and deploy the model, we identified the top challenge in each of these boxes. Yeah, so what you see is that when you go to critical deployment and creating models, then many companies are experiencing challenges around scaling the machine learning and deep learning pipeline. And if you talk about training and evaluating for critical deployment, it is reproducing models and debugging deep learning models is actually quite challenging in these contexts. Last year, so I'm really going from 3 years ago to 2 years ago to last year, we published a paper. Lucy was then a postdoc with us. She's now a postdoc at the University of Helsinki that we published in IST, where we identified several of the machine learning and deep learning challenges, anything from data dependencies to serving infrastructure to how do I train at the edge, etc. And this is a bit of a literature review, but purely based on publications describing machine learning systems that have actually been deployed in real-world settings. And if you put the deployed in real-world settings as an inclusion criterion or an exclusion criterion, if that isn't the case, then the number of papers is actually surprisingly limited because many people are still in the prototype and experimentation phase. The implications for architecture around ML ops or machine learning, again, I try to capture 3 of them. The first is that heterogeneous hardware, many of these systems that use machine learning and deep learning models, they do not just have a CPU on the deployment architecture, but they often either add GPUs, they add FPGAs, they add ASICs or other kinds of things to allow for much higher performance of their systems. So we need to focus on the fact that we're not deploying on a traditional CPU-only architecture, but actually heterogeneous architecture makes the deployment architecture. Yeah, all of you know Philip Christensen's 4+1 model. The deployment architecture is one of those views. And that view is now actually becoming much more important. And it's surprisingly difficult to build software that gracefully deploys in a heterogeneous hardware context. Second, some of my colleagues at Chalmers and Gothenburg University are looking into assessing and designing different quality attributes of machine learning and deep learning models. And this is still an open and very difficult problem. That is, I think, quite an important one from an architectural perspective as well, because, you know, as architects, our job is to get the quality attributes of the system right, and that is not just the high-level subsystem kind of stuff. This sometimes requires architects to go very deep into very specific aspects if those aspects have a outsized impact on the quality attributes. And then finally, especially in embedded systems contexts, I see that federated learning is becoming an increasingly important topic for all kinds of reasons, if only because a centralized infrastructure where you collect all the data to one central location and do all the training in the central location and then push out the model to all the systems in the fields in an MLOps context is becoming prohibitively expensive if you look at the amount of data and electronics that you need to have in place in order to be able to run this in a central location. And then federated solutions can actually be much more cost effective than traditional ones, traditional more centralized ones, but there is a significant architectural challenge around this as well. As I mentioned in the beginning, I wanted to spend a minute on what are we doing at the around AI engineering. Here, what I wanted to mention is that experimentation and prototyping is, well, first of all, we see companies moving towards a evolution model. They start with experimentation and prototyping, and many companies are still there. Then there is non-critical deployment of machine learning and deep learning components. Then there is critical deployment of machine learning and deep learning components. Then there is cascading deployment of machine learning and deep learning components, and then fully autonomous machine learning and deep learning components, where basically models are tracking their own behavior, they can trigger their own retraining, they know how well they're doing, they can generate warnings when their performance starts to fall outside the boundaries of what they had initially intended, etc., etc. What we did between the person I mentioned earlier, Helena Ivica-Čenković, colleague professor at Chalmers, and myself, we put together a research agenda where we basically followed the data science structure, and we focus on the challenges that we see in each of the key areas. So around assemble the data, it's data quality management. We discussed that. Around models, it is around design methods and processes, because in most AI, machine learning, data science context, when you ask people, how do you end up with that model? They will basically say something along the lines of, well, I had some experience of things that I'd done earlier that worked well, and I just experimented my way towards this one, which is very unsatisfactory from a software engineering perspective. Model performance is a big topic, and then deployment and compliance. And then you can see it around AI engineering. We defined some challenges around architecture, around development, and around process. And then we identified that there are also challenges in the context of domain-specific AI engineering. For instance, around cyber physical systems, you see that federation is a big topic and heterogeneous hardware. For safety critical systems, the data trail, explainability, how do I validate for safety are big questions, reproducibility, of course, as well. And then around autonomously improving systems, think reinforcement learning and other kinds of approaches. It is really, how do I generate data that doesn't require pre-processing? How do I think about automated experimentation? How do I think about the system evaluating its own behaviors? Multi-armed bandits is one of those typical classes of reinforcement learning algorithms that you can use here. And then exploration versus exploitation is one of those interesting ones. In a real world production environment, how much do I allow a system that is supposed to become better to explore the space of all possible things that it could do in order to get to a good outcome? And to what extent do I just want to exploit what I have learned so far? And what we've done is that over the last several years, we've built up quite a nice team. David is working on autonomously improving systems. Yuchu, an industrial PhD student from Volvo Cars, is looking into A/B testing. Iris, an industrial PhD student from Siemens, is looking into federation, generating insights from operational data and generating strategic insights. We have Aishwarya, who's looking into data pipelines, data versioning, and dependency management. Lucy is looking into monitoring and logging, Theodore into labeling, Hugo is looking into heterogeneous hardware, and Manu is looking into design methods and processes, and then finally Hong Yi is looking into federated learning and reinforcement learning. And if any of you want to learn more about that, then of course don't hesitate to reach out to me. Finally, conclusions. I'm not sure who of you knows this gentleman. He is George Colony, CEO of Forrester Research at the time. And he had this quote, "In the future, all companies will be software companies." I think he got it almost right. I think that in the future, all companies will be digital companies, because it will not just be about software, it will be about data and about artificial intelligence as well. Those things are really becoming inherent and critical parts of our software systems that we are building these days. As conclusions, I will recap the three takeaways that I mentioned earlier. First, this software is really complemented. So traditional requirements-driven or specification-driven software is really complemented with data-driven and artificial intelligence-driven functionality. And this results in us not just having to deal with DevOps, but also having to deal with data ops and ML ops. This fast feedback loop that the ops generate for us allows us to work much more quantitatively, and we can really start to move towards measuring the effects of architectural design decisions. I think that this is an important development that is quite interesting and exciting. And then finally, data-driven and artificial intelligence, machine learning and deep learning-based functionality, they add new types of architectural challenges that we need to address as a community. I know I did raise some of these architectural challenges under each of the DevOps, and MLOps, but I still think that I'm only barely scratching the surface, and there's quite a bit of need into better understanding what the data and data pipeline and the machine learning, deep learning model integration into software intensive systems, what the architectural challenges are that we need to address here. For those of you that felt that this was interesting, I have a bad habit of occasionally writing shorter and longer books. Speed Data and Ecosystems is a book that is a few years old now. Talks about some of the concepts that I described in this talk. You can buy that on Amazon or CRC. The two middle ones, using data to build better products and impactful software, I give away as PDFs. The book on digital transformation is a little bit more for business leaders. I give that one away for free in PDF, or you can buy a paper copy from me if you're interested. And with that, I would like to thank you very much for listening to this talk that became a little bit longer than what I had intended. But if you're interested, you can follow me on LinkedIn. Of course, I'm also on Twitter, although not very active. I publish articles on Medium as well, and the same articles end up on my blog. And I have a newsletter there as well. So if you're interested, feel free to subscribe and listen to or read what I'm up to more recently. And with that, thank you very much. And I look forward to discussing some of these topics with you on the summer school sessions on, I think, June 15th, if I'm not mistaken.